Yes, my talk will be about a particular part of what Thomas has said about this protein structure prediction problem. Namely, it will be about a new general approach to model these protein angles, and we call it Sine-Skewed distributions for protein angles. And this is joint work with José Amejeras Alonso, who is now also here with us, formerly still at the Katholieke Universiteit Leuven as a postdoc, and who just now took on very recently a professorship at the University of Santiago de Compostela, for which I would also like to congratulate you. So my talk is foreseen as follows. I'll start with some motivation, and then why the need for these models. Then I will talk about what inspired me to propose this model for protein data. Then we will come to our proposal, the Sine-Skewed toroidal distributions, and finally application on protein data. But before starting this plan, I would first like to say a few words about my journey in directional statistics, because this is strongly related to Kanti Mardia. And since we are celebrating his birthday, I would also like to say a very few words. So basically it was around 2011, 2012 that I entered the field of directional statistics with my colleague Thomas Verdevoux, and well, as a young postdoc, so I was getting to read a lot about it, and I saw these big names like Mardia, Jupp, Kent, and so on. And so we wanted to go to a laser workshop, and we went to the laser 2013 workshop. We did not yet get into one of the speakers slots, but we could present a poster. So both Thomas and me, we went there with a poster, and this is the poster that I presented there. And well, you know how it is. Very often at poster presentations, you're waiting there for a long time. Not much happens, and you get like, oh, I would have preferred to give a talk. But then at some point, Kanti actually showed up, and well, he took a look at the poster, and we had an interesting discussion about it. And he gave very encouraging words, saying that, oh, this is good work. Continue in that vein. And I would like to say that this was really like a very strong motivation for me to actually pursue into the direction of directional statistics. And so around that time also came the idea, when Arthur Pusey was visiting me and Thomas in Brussels. We had the idea, oh, there is this great series of laser workshops, but as Kanti said, they are not totally focused on directional statistics. So we had the idea of making something that is completely focused on directional statistics. And so with Arthur, we came up with this idea of the ADISTA workshops, the first taking place in 2014 in Brussels, the second one in 2017 in Rome, together with Francesco Lagona, who also joined later today, well, who is now here, but joined after a little bit later, and Giovanna Iona Lasigna. So this was the second one. The third one to be organized, well, now hopefully in 2022 with Rosa Crujeras. And this is a picture that was taken during the 2017 edition in Rome, where I was very happy to have some fruitful exchanges there with Kanti about our forthcoming Wiley paper. And so Kanti mentioned them already, our two books about directional statistics. On the left-hand side, the book that we wrote, and on the right-hand side, the Applied Directional Statistics, Modern Method and Case Studies. This was an edited volume. So the journey had went on from the poster to the two books, and there's one person indeed that made a double contribution to the Applied Directional Statistics book, who contributed 2 chapters, and that is again Kanti Mardia, who was so kind to give us 2 contributions for our book, for which I would also like to thank you. So it clearly shows that I also have been very much inspired by Kanti and his work and his encouragements. And this is also what brought me here today to be part of this nice symposium. Now, really, to the talk itself and to the motivation. So it was already mentioned by Thomas, so I don't have to give my layman explanation of what protein angles are. So basically, you have seen the new approach popularized by Thomas Hammerich and the link between the protein structure prediction problem and direction statistics. And so what I'm concerned here with is the fact that pairs of dihedral angles are data on the torus. And so logically, if you want to work with a model on the torus, you need a distribution on the torus. So that is the main goal of this talk. Of course, there exist quite some proposals in the literature. And one of the most famous toroidal models is the so-called bivariate von Mises density, which has been proposed by Mardia in 75. It actually arises as a maximum entropy distribution, and it has von Mises marginals. So it is really a two-dimensional extension of the classical von Mises distribution. And so here I wanted to put everything on a single line, so this is why I had to use footnote size, no, even tiny, to put everything on this line. And so here you can see, this is the density. C is some complicated normalizing constant. We here have the first part in the first component, the part in the second component, and then here, this is the mixing part, the part that creates the dependence between the components θ1 and θ2. Of course, mu1, mu2 are the location parameters, kappa1, kappa2, the concentration parameters. And it is this 2x2 matrix here with 4 parameters that creates the circular dependence. And so this model has a lot of parameters, which implies that it led to several submodels that have been proposed from this general model. And on the next slide, I'm showing what some of the densities of these submodels look like. Here on the top left, for instance, you see something that is called the Rivest submodel by Louis Rivest. This on the top right is the so-called Sine model, and that is the model that Kanti has mentioned, this paper in 2002 by Singh et al., who used direction statistics to model protein data. Then here on the left-hand side, another particular case is the so-called cosine model from Kanti and co-authors. And this is another model that I and Jose, we termed the independence model, because yeah, you just make the entire matrix A disappear, and then you can clearly see that the two components work independently. There is no common behavior between them. So this gives you some idea of what these different shapes of the bivariate von Mises can look like. Another recent, and I would like to say really nice proposal, is from Shogo and Arthur in 2015, where this time they put their focus not on the von Mises, but rather on the Repdt-Cauchy, which is another very famous distribution on the circle. So their proposal, I will show the density later on. It has Repdt-Cauchy marginal distributions and Repdt-Cauchy conditional distributions, which is quite a rare fact, because typically you either have nice marginals and then more complex conditionals, or the other way around. And in their model, it actually happens to be the case for both of them. So this is a pretty nice alternative distribution on the torus. And their model is based on a copula-like construction that has been initiated by Whaley and Johnson, and has also been later refined, the general copula-like construction by Jones, Pusey, and Kato. Now, all these models that I've shown, this model and these models here, they share a common feature, which is that there is some form of symmetry, you may call it central symmetry, around the location on the torus. And we can clearly see here that these distributions, well, they all have some type of symmetry around the central location. However, many data sets actually happen to be non-symmetric. And here I'm quoting Kanti from his famous 2013 GRSSC paper, where he writes in the context of protein data, and I think this is one of the challenges that he presented there. Another unexplored area is constructing plausible bivariate skew distributions. The field is still evolving, but it should be noted that for bioinformatics, we generally need computationally efficient methods. So that was the challenge, and we wanted to take it up to propose a bivariate skew distribution, so that goes beyond the symmetric models, but that is also computationally feasible. And well, so that's it for the motivation. How did we choose how to build this model? And there comes the inspiration. So we went to look at on the real line, because on the real line, well, you have many proposals for creating asymmetric distributions. There have been transformations which were proposed as early as the end of the 19th century. You have mixtures, you have two-piecing being the idea that you take a symmetric distribution, you cut it in two halves, you add different scaling parameters on each half, and then you glue it back together. Integral probability transforms, variance mixtures, and so on. Many more exist. And then there is modulation of symmetry. Modulation of symmetry goes back to a paper in 1908 by Fernando de Alguero, who tragically died in an accident due to an earthquake the same year. But this model has been rediscovered over the time. And the landmark paper that really put it in the hearts of statisticians was Azzalini in 1985 in the Scandinavian Journal of Statistics, where he has developed his famous skew normal distribution. So this is the density here. Phi of x is the standard normal density. And what is this modulation of symmetry? Well, symmetry is displaced by multiplying the symmetric density by some skewing function. And here the skewing function is capital phi, which is the cumulative distribution function of the standard normal, of lambda times x, where lambda is a skewness parameter. Now it is not hard to see that if lambda is equal to 0, we have phi of 0, which, well, is equal to 1/2. So we fall back on the standard normal. And for any other values of lambda, you will get an asymmetric distribution. I'm not showing you it in the one-dimensional setting, but I'm showing you rather a picture in the two-dimensional setting, because this proposal has been extended to higher dimensions, mainly by Azzalini himself in a 1996 Biometrica paper, and then also in a GRSB paper, and well, other people, including Mark Jensen, who has been very prolific in this field, have taken this to the k-dimensional setting, where they proposed multivariate skew symmetric distributions. And here is what you can see. This is one example of such a skew symmetric distribution. What has happened here? Well, basically the modulation of symmetry means that the probability mass is pushed here in this direction, in this direction of the parameter lambda. So here we have a skewness vector and it goes into this direction. So you can see that the probability mass is displaced into the direction of the parameter lambda. That is the idea behind modulation of symmetry. And now symmetry modulation in the directional world has taken place in various steps. On the circle, there were two papers who were done independently, but well, due to different times in publications, they appear to be subsequent, but they have been done at the same time. So Umbar and Jawanabadaka in 2009 and Avi and Pusey in 2011. Then on the sphere, Thomas and myself reproposed the symmetry modulation in a 2017 paper. Actually, this was the idea for this also came up during the 2013 laser workshop. Then I would also like to mention a general discussion on manifolds of symmetry versus symmetry modulation, which has been done by Peter Regoli and Azzalini, also in GmbH. And correct me if I'm wrong, Peter, but I also believe that this paper has also taken its origins during this later 2013 meeting, because that was at the time when the organizers had invited Adelchi Azzalini there, precisely with the goal of bringing skew models into the directional field.
You are correct.
Okay, great, thanks. And I was very happy because before working in directional statistics, I have been working in precisely on these symmetry modulation things. So actually, Azzalini happened to be the only person that I knew at this conference, and so the idea came a little bit independently, but at the same time. And then on the torus, well, it is this paper that I'm presenting now with Jose that gets. And later today, during another talk by Najme, you will hear some further extension in this direction. All right, so now let's get to see our proposal. You will see it is very, very simple. Here we go. So basically this here I denote by f of x minus mu var theta. I don't know how to call this symbol, but in LaTeX it is var theta, so I'm just calling it var theta. This is the base symmetric density. So this can be any of these toroidal models that I showed you before, where mu is the location around which we have symmetry, and var theta contains all other types of shape parameters, mostly of course concentration parameters. And our approach simply consists in transforming this density into that density here. So you multiply it by a skewing function. So our skewing function is of this form here. It's an additive term where here we are in a d-dimensional setting. So we describe it for a general d-dimensional torus, but of course the main example is when d is equal to 2, the typical torus on which we will also see later on our application. So well, we just multiply it by this sum of lambda s times the sine function. And so lambda is a d-dimensional parameter that plays the role, of course, of skewness parameter. When lambda is equal to 0, well, this part here simply becomes 1, and we are back to our initial symmetric density. And the parameter also needs to satisfy this constraint here to make sure that we still have a valid density, that it remains positive. Otherwise, this is not given. Now, some direct observation is that the parameter has a quite simple interpretation in the sense that when lambda is 0, we have symmetry, otherwise we do have asymmetry. Now, very important is that the normalizing constant is unchanged. And this is a non-trivial fact because very often when you work with toroidal data, or more generally, when you work with directional data and distributions, it can be a pain to calculate the normalizing constant. With this construction, you are free from this. You can simply see that, well, it's a simple exercise to see that this integrates to 1. So there is no normalizing constant that needs to be calculated. And also, interestingly, when d is equal to 1, this gives us the sine-skewed circular densities that had been proposed by Umbach, Yamanaka, Abe, and Pusey. And here I'm sparing you the different details of, theoretical work that we did in our paper, just referring, if somebody is interested, in that paper, we do provide expressions and we say something about marginal distributions, conditional distributions, trigonometric moments, shape measures, and dependence measures. But they are too lengthy to be presented here on slides. So for those who are interested, everything is in the paper. What, however, I would like to show is the important part of being able to generate data from this distribution. So here you have the slide about random number generation, which also happens to be quite simple. So suppose that you know this is something that is necessary. Since we propose a general approach to skew any existing toroidal distribution, well, we of course also assume that you have a way to generate random numbers from the distribution we start on. So that is the first step. Simulate a random quantity from the distribution associated with your favorite symmetric toroidal distribution. Independently, generate also a random number ui from a uniform distribution on 0, 1. Well, that's a very easy step. And then our new data point from our sine-skewed toroidal distribution is then given by this very simple construction. So we have this condition, if our uniform number is smaller than this quantity here, and there you see appear the quantity that is present here, so our sine skewing quantity. If ui is smaller, then simply take the value yi. If, however, ui is larger than this quantity, then take minus yi plus 2 times mu, the center. And by doing this simple procedure, which is very fast and efficient, you will be able to generate data from our sine-skewed toroidal density. So this is a nice feature that you can easily generate random numbers. Here I will briefly discuss 3 special cases to also show you what these densities look like. So as I already said, a very easy, a very simple but also famous particular case of the bivariate von Mises is the sine model proposed by Singh et al. In 2002. The density looks like this. So you see, you recognize this part from the bivariate von Mises, and now you see that here, this is what I think why it is called the sine model, because only a sine part is left. and R is the dependence parameter or correlation. This is the symmetric version with this normalized constant, and well, you easily get the sine-skewed version by just looking at this multiplication here. And in the bottom, you see a little bit how this skewing effect takes place. So these are the parameters. They are the same in both the parameters that stem from the sine model. And here on the left-hand side, I'm indicating what skewing parameters we take. So the skewing parameter in the first component is the same, 0.3 on top and below. But you can see that on top, the skewness parameter for the vertical part is 0.3 compared to 0.7. It becomes stronger in the picture below. And we can see that more probability mass is pushed into this direction here. But that's for one particular case. For the second one, I'm not showing plots, but just indicating you this is the density of the cosine model of Mardia et al. So where we recognize our steady part, and now we have here the cosine part, which is why one calls this the cosine model, which again is easily multiplied by this skewing function. And here you have the corresponding normalizing constant. And for the third special case, I announced it previously that I would give the density of the bivariate of the Kato and Pusey model, and here it is. So these two lines are the expression of their model, of their symmetric model. You have to see this here as 1 divided by this quantity. This is why I have put all of this to the power -1. So this is their symmetric model. It contains cosines, it contains a product of cosines and a product of sines. And here you see the expression for, so there are various constants that appear in their distribution. And so here's the explanation of what it is, although this part here has slightly dropped out of the picture. And again, we multiply it by our sine skewing mechanism. So if you're interested in this expression, well, it appears in general in our paper, but of course also this is the paper of Kato and Pusey 2015. And here I'm showing a little bit different shapes that you can get. It's again the same procedure. From in the top row we have a smaller amount of skewness into the vertical direction, while on the bottom row, in the horizontal part, we have the same amount of skewness, but a strong amount of skewness into the vertical part. And this time I'm showing a little bit more different shapes because I'm also varying the parameters of the original symmetric model. And you can see again the mass shift that occurs. Now, how about inference? Parameter estimation is not complicated. It works simply by maximum likelihood principles. Of course, you need to revert to numerical methods because otherwise you're not able to get you don't get concrete expressions for the maximum likelihood estimates. And we need here nonlinear optimization methods because we have to satisfy this constraint here. The constraint that makes sure that our parameters are in general smaller than 1. So that's why we had recourse to the R-Sol-NP package in R, and we used the solver proposed by Ye in his PhD thesis from 1987. And this is a suggestion that comes from José to use different initial points to avoid having a local maximum as a solution. And what we also do, and what I also spare you here, is we also provide asymptotic distributions of our estimators, and we also build tests for symmetry, which is of course very simple. I mean, it's like submodel testing. We just put the different parameters to 0, and then you can test whether the original model or the sine-skewed model gives a better fit for your data at hand. So finally, we come to the application on protein data. And so here a brief data description. These are data that we got from Thomas Hammerich. They stem from the Top 500 database, which is a selection of 500 files from the so-called protein data bank. And they are of very high resolution. And so here, a brief explanation that in these data, all proteins with chain breaks and PDB files that caused errors were removed. And also amino acids with a C or N terminus are not employed. So this is really for those who know about these data that I put this detail here. what I would like to say is that we analyzed a total of 20 different amino acid types. I'm going to show you plots of of two such amino acids, but in the end, I will show a table where we made the full analysis of all of them. Now, you can see if you take a scatter plot of these data, you can see that a unimodal distribution will not be enough. You would definitely need a bimodal distribution. And well, with our construction of Sine-Skewed modeling, sometimes you can get a unimodal, sometimes you get a bimodal construction, but they are not by nature multimodal. But this is why we said, okay, for analyzing these data, what we need is a mixture of our flexible Sine-Skewed models. And so this is the type of mixture that we look at. We took here G1 and G2. They are different Sine-Skewed toroidal densities that we have shown you before, and P is the mixing proportion between the two of them. And just for an explanation, the word Ramachandran plot is actually a scatter plot for protein data. It has been proposed by Ramachandran in 1963, and from what I understood before, Thomas had the idea to put probability distributions on the dihedral angles. Those were mainly done from visually looking at these Ramachandran plots. And also here in our mixture model, the parameter estimates, they were done by adapting our optimization approach, taking into account not only the constraint on the lambdas, but of course also the constraint on P that has to lie between 0 and 1. Okay, and so here in this table, I'm showing you which model has been chosen for each of the 20 different amino acid types as the best model. And whenever you see an S before, this stands for Sine-Skewed version. C is the cosine model, VC is the wrapped Cauchy, so the model by Kato and Pusey. S is the sine model. And so we can see here that nearly everywhere a Sine-Skewed version has come out as the best model. And what I mean by that is that we have used twice the same Sine-Skewed distribution in our mixture. So there would even be room for further improvements if you would look at mixture components, but we wanted to make it simple for the sake of comparison. In a few, so actually this one here, that one, and this one, in a few there were two models who came out as nearly equally good. And so those were the instances where also symmetric models turned out to be pretty good. So what we then did is that for these cases like here, we made our symmetry tests or our submodel test. So we were testing here the cosine model against the Sine-Skewed cosine model, and we got a p-value of 0.01. Here we were testing the sine model against the Sine-Skewed extension, and we got this quite low p-value. And well, here we did the same, and we also got a very low p-value, which overall shows that the Sine-Skewed extension allows for a better fit of these toroidal data. And here, yes, to give you an idea of what these data look like, here you see the Ramachandran plot, or simply the scatter plot, together with the mixtures of our Sine-Skewed versions. And here, well, you can see that indeed the data are bimodal or even multimodal in certain instances, and you can see how the model flexibly accommodates these different data hubs. All right, so that's all that I wanted to show. More information on this topic will later follow in a talk by Najmi. And yes, I would like to thank you for your attention and also again wish Kanti a happy birthday. Thank you.
Okay, thank you very much for that talk. I'm gonna knock already, or we can applaud. So we've got some time for questions. Go ahead.
Hello, John Kent here. Very, very nice presentation. What it reminded me a little bit was the work by Bachelet in his book of many years ago, where he was, if my memory is correct, he was also trying to develop models for skewed distributions. Mm-hmm. And his method was a more cumbersome method because he would take sines of sines, that is a sine of x sort of function, And it was even more awkward than the constructions you were dealing with. But it might be worth having a brief look at that to see if my memory is right and see if there's any further insights that he might provide. Another thing that occurs to me from your talk is that in Azzolini's construction, he had this skewing parameter lambda, and he didn't have to do anything special with that. It was just a real number. In fact, you could even look at the limits as lambda goes to, well, 0 and plus and minus infinity, and it made some sense. In your case, you had to put lambda explicitly between -1 and 1, or 0 and 1, in order to make sure you had positive probability densities. And that seems a very awkward sort of constraint. And I just wondered if there was a more elegant way of incorporating that idea.
Well, thank you very much. So first on your remark about Bachelet, yes, indeed. I think the Bachelet construction, if that is the one that you have in mind, but I think it is that one. It would fall, if I go back here. This would rather fall under the form of scale transformations, of which 2-piecing are a special case. There it is. I think it's a paper in 2012 by Arthur and Chris Jones, who on the circle have actually extended the proposal of Bachelet by proposing general scale transformations.
You have permission as co-host. Maybe you have to click the ... or something that there is record.
Kanti is having someone talk in the background. I will mute him. Okay.
Okay, good. I actually thought it was perhaps Arthur who was saying something about this. So yeah, that's what Bachelet did. We also had been thinking of if this could be used. Did not really clearly see how one could do this easily also on the torus, this construction. And now for your second remark, yes, this indeed here there is no constraint on this model, no constraint whatsoever. In the d = 1 setting, so on the circle in this original model, there is also some sort of constraint which says that their lambda must lie between -1 and 1. So our constraint is in some sense inherited, if you want, from the circular part. We had also been thinking about, would it not be possible to go for some kind of multiplicative structure like 1 plus lambda 1 sine times 1 plus lambda 2 sine and so on. That would not put this summed constraint, it would put just this constraint here, that all the lambdas must be between -1 and 1. We did not want to go for that one because it did not lead to so nice constructions in the end. This is why we had to, we went with this model, which has indeed this this constraint on it. We could not see a simpler way to construct it without having this constraint. But of course, if somebody would come up with a constraint-less model, I think this would be certainly easier to handle when it comes to inference.
Thank you.
Okay.
So I have a question. Well, thank you very much, Christophe, for your nice talk. I was wondering actually regarding one of the things that you have just commented right now about the multiplicative structures, because I thought that another possible way of constructing this skewing was to reapply the well-known sign skewing trick that is done for univariate densities to the torus in a multiplicative fashion. I thought that was going to be simpler than to do this in this additive fashion. So I was wondering if you could comment out a little bit more on the complications that you might have if you go through the multiplicative approach.
Yes, so with the multiplicative approach, I think one of the problems that we had is that then you are not so, it is already not so clear. If you go with the multiplicative approach, you would already need to make a check for the normalizing constant, because then you are no more in this setting. You have a sine times sine that appears at some point, which makes it which balances it a little, takes the balance a little bit out. And also you have for other properties, you get very, I mean, with the multiplicative approach, you get very long expressions, which make calculations, which make them quite hard. This is why we went for this additive fashion, which eases the calculations and also eases the final expression of it. Then, of course, you could also think of going for a copula-like construction where you choose some general copula and you would skew the margins individually. That's something we have not taken a look at. If that would, I mean, of course, in the end, you would have a copula construction, which likely would be a more complex form, but I cannot say more on this because we haven't looked at it.
Nice. I also have another question if time allows. I don't know if that's possible.
Yeah, we're gonna make one more question.
Okay, it's regarding the data applications and the mixture feeds. If I understood correctly, you used 2 components. Is that correct? I was wondering if you explored further and beyond that, just going for higher number of components, because it might be the case that actually the minimum bias is attained with 3, for example, or further. Yeah. So
we have been thinking of that indeed, but we left it here at the 2. But we had been thinking later on to because for 2 it already gave a quite reasonably good fit, but we had been thinking, okay, should we not perhaps go for a larger, for even a third? I mean, you could use AIC, BIC also for searching for the ideal number.
Yeah, sure.
Yeah. We then had said, okay, we would rather postpone that for some future.
Yeah. Also, I think a real comparison here will be to run this kind of search for the optimal model in terms of the BIC with allowing an indefinite number of components and comparing it with the bivariate cosine von Mises model, or bivariate sine von Mises model, which is the reference one, in order to see whether this idea of extending the distribution in the torus from the 5 parameters that has the bivariate sine von Mises, if I'm not mistaken, to the 9 parameters that your skewed distribution has, if I'm not mistaken, well, really makes an importance in the practical fit.
Yeah. So so here our goal was really to compare the classical models on with our sine skewing, and we could see that for this comparison, indeed, it led to a clear improvement. But yes, a more general comparison definitely should be done, and also then in that comparison we would like also to add the proposal by Fernandez Duran, who also has a more complicated construction, but nevertheless would also be something to be added. And
the non-negative trigonometric sums, you mean?
Exactly, the non-negative trigonometric sums.
Okay.
I'm not sure. I just
we will laugh. Yeah, I mean, I think they're quite flexible, but maybe you're prone to have more modes.
Yeah, that's what we think as well. We will take a look at that, and we were also thinking for actually employing. I think that's. I know that you have developed a goodness of non-parametric goodness of fit test for cylindrical models. I think also one exists for toroidal models. No.
Yes, I think that could be applied, but
yeah, just to see also.
I don't know. It's just I was just wondering about a comparative approach with other methods.
Yeah, no, but this is what we had in. These are the things that we have. We do have in mind. Yeah.
Thanks.
Thank you.
Okay. Actually, by the way, if we're talking about these trigonometric polynomials, I was thinking I've done some stuff with the trigonometric polynomials, and I think Fernandez Duran, what he did, the constraint that he has to ensure the non-negativity, I think that sounds pretty expensive, and I think what I've been doing on that is that instead of approximating the function directly, one can approximate the square root of the function using a trigonometric polynomial and then square all values. This always gives you something non-negative. But we could talk about that offline, so we can head on for the next talk that's scheduled now.
So I stopped sharing.
Okay, then Ola.